Swayam Prabha. Digital India. Educated India.
So now, by taking this same equation for a steady flow, okay, for a steady flow, the changes in the system must be equal to the net property transported by the mass across the control surface. Okay, so we can write down that the change in a steady flow, right? When we are talking about steady, what does it first of all indicate? There is no change over time. Okay, if we say there is no change over time, then what will happen to this term d by dt? It will go to 0, or it will not be able, it will not be there, so it disappears. So finally, for a steady flow, we can tell that the change is only due to the net change that is happening across the control surface. Okay, so there is no change within the control volume, it is only the flux that is going out minus the flux that is coming in. Okay, that is the net change. Okay, so I can write down that d by dt of the P system is equals to outflux minus influx of the extensive property. Okay, so now we can write down in the Newton's second law that summation of forces is equals to the rate of change of the momentum, right? So you have rho mass into velocity, so if you just take dv by dt, that is your acceleration, so mass into acceleration is your force. Now we are just discretizing and writing in integrated form. So if you look at that, then it is d by dt integration over the whole system rho v dv. Okay, so that is going to give you the total force or the summation of the forces. So basically we can write down the sum of all external forces acting on a system is equal to the time rate of change of linear momentum of the system. So you could see that again I am just trying to explain that the sum of external forces acting on a system is equal to the time rate of change of linear momentum of the system. If you look at this is nothing but your linear momentum. Okay, so if we take the time rate of change of linear momentum, that is going to give us the forces. So from here we could derive the linear momentum equation. Okay, from this concept we could derive the linear momentum equation, and in fact the linear momentum equation is already to some extent shown you, but we will see that in details. Now we have already discussed that Newton's second law can be expressed like this. Okay, now if we look at this statement which we said, and we will write down the Reynolds transport theorem. Okay, so if you write down the Reynolds transport theorem, that provides you the necessary tool. Okay, now if we write down summation of the external forces, that is equals to d by dt of the momentum over the system, and we know that to convert from the system to control volume, we will write down that d by dt of the momentum, change in momentum within the control volume, plus the change in momentum over the control surface. So we could write down that the d by dt of rho v dv over the system is equals to d by dt rho v dv over the control volume plus integration over the control surface rho v dot n, because we are trying to get the flux out of the control surface or into the control surface. So we are taking the normal velocity. So that is v dot n dA. Okay, so you may take elemental area and then find out what is the momentum or the flux, and integrate over the control surface to get the total momentum that is passing across the control surface. Alright. So this equation is nothing but your linear momentum equation. Okay. Now if I take this equation and I will be able to write down what is the equation for steady flow, which we have already seen. So for steady flow, the temporal derivative is going to be 0. So I can write down summation of all external forces is equals to the change of momentum or the total net change in the momentum in across the control surface. And what is that? That is nothing but the outflow momentum minus inflow momentum. Okay. So this equation or this statement is nothing but your linear momentum equation. Okay. And for steady flow, you can very quickly apply this linear momentum equation or concept and find out the forces. Now, if I take the forces acting in the x direction, I will find out what is the outflow momentum in the x direction minus inflow momentum in the x direction. That gives me the total force in the x direction. So similarly, if I will take y direction, I will also take outflow momentum minus inflow momentum in y direction. That will give me the force in the y direction. So in most of the cases, you may not require to go and find out what is really happening within the control volume. It may be quite complex, it may be complicated, so you really don't need to understand that. Still you can find out what is the total force being exerted by a fluid flow within that whole complicated system just by taking a suitable control volume and find out what is the outflow momentum and what is the inflow momentum, and that gives you the total force. We will actually find out in a couple of more slides that how beautifully this concept is being applied, and you can find out the forces exerted upon various sections or various bodies due to the flowing fluid. Okay. So now we could say that information regarding the condition within the control volume is not needed to find out the force. Okay. So the surface integral automatically takes care of the sign, and the integral gives the mass flow rate directly. So if you take the velocity normal velocities at each point, it will automatically give you the outflow and inflow momentum. So you really don't need to bother about the sign conventions and all. You can take one reference and do the calculations to find out the outflow momentum and inflow momentums. We will see that during applications. Okay. So now let us look at a couple of applications of the linear momentum equation. In this, first, as we discussed, you have to define a control volume. So the finite control volume has to be defined first. Okay. So let us take a simple problem. There is a flow through a pipe, and the pipe, if you look at, this is having a different diameter here at section 1 and different diameter at section 2, and the flow is taking place from this side and it is going out on the other side. So now let us say there is a velocity v1 here and there is a velocity v2 here that is going out of the two faces. Okay. Here it is coming in with velocity v1, here it is going out with velocity v2. Now if I want to find out what are the forces that are acting in the x direction, okay, if I want to find out the forces acting in the x direction, what can I do? I have to find out the discharge and multiply with velocity. That will give me the what? Momentum. Okay. So if I take the discharge and multiply with the velocity, then that gives me the momentum. And if I take the discharge and multiply the velocity in a particular direction, that gives me the momentum in that direction. So now here, if let us say I will take the point cross section 1, at this cross section 1, I have the velocity in x direction as vx1. Now if I multiply vx1 with q, then that gives me the momentum at at section 1. Similarly, if I take vx2 and multiply with the discharge, that is q, that I will get the momentum at section 2. So if you want to calculate q at two different places, you can do that, which is nothing but your area multiplied by the velocity. So if you take this area and velocity v1, you will get the same q, which is going to be obtained by taking this area and this velocity v2. Okay, so q is not going to change, discharge is not going to change, which is going to remain same because it is incompressible flow, right? So now if we write down the force that is acting in the x direction, this is a curved pipe, and in this pipe, let us say I want to find out what is the force exerted on this pipe in the x direction. So I will be able to write down that summation of f of x is equals to the outflow momentum, that is rho 2 a2 v2 into vx2 is equals to rho 1 a1 v1. Both will be same, but if it is compressible, then it might be different. Okay, so we will find out the outflow momentum minus inflow momentum, that is nothing but your rho q vx2 minus vx1. So this simple expression, if you know what is the discharge, you know the density, you know the velocity at two faces of the control or the surface of the control volume, then you can find out what is the force that is acting by this flowing fluid on the pipe or on the surface. Okay, or if I can say that, okay, what is the reaction that is being exerted by the pipe on the flow. This statement says that for most applications we need to find out a control volume in such a way that the flow leaving and entering are normal to the control surface. Okay, so basically what it says, you have this face and you have this face. If I say that I will choose this control surface or this face and this face in such a way that it is going to be normal to the flow direction, then I really don't have to find out the directional or the velocities in different directions. So I know what is the normal velocity, I can quickly use that and find out what is the flux coming in and going out. Okay, so that will be useful. We'll see that in more applications. Now when we look at the control volume, if you look at, in this case, how did we select the control volume? We took this as one surface and this as another surface, and although we did not mention, the other surfaces are actually going, I'm drawing this line which is not really going along the pipe, but this pipe itself or the boundary along the pipe is showing me the other two surfaces. Okay, so this is nothing but my control volume, and the flow across this boundary is 0, across that boundary is 0, so we don't need to bother about. We only know that the flow is coming in from here, going out from here, so we are taking the flux going outflux and influx along these two boundaries. Okay, so it is easy to take suitable control volumes and solve the problems. Okay, so let us look at another problem now. If you look at this, okay, there is a jet that is impinging the fluid, or the flow jet is impinging on a surface which has some kind of projection or outcrop which looks like this, and that divides the flow into two separate streams. Okay, so a flow is coming, it hits this projection, and the flow is splitted into two parts, and that moves in two different directions. Now let us say I want to find out what is the force that is going to be exerted on this surface or on this wedge shape, or what is the reaction that is going to come from the wall on this fluid. So I can find out how, by taking or by applying the same linear momentum principle. For that we need to find out what is the discharge as well as what are the velocities in the respective directions. So now I will choose the control volume first. Now to choose the control volume, as I said, I should try to make it normal to the flow direction as far as possible. So here this line is normal to the flow direction, and here in between this and this, how you take it doesn't matter. Then here it is again normal to the flow direction. I have come along this, Now here also it is normal to the flow direction. So if I take this as the control volume, the dotted red line is my control volume, then I can say that from here to here there is a flow or there is a flux. From this to this there is a flux. From this to this there is a flux. All other places there cannot be any flux. All right. So if there cannot be any flux, I don't have to worry. Okay. So I need to calculate only those locations, only those surfaces where there is a flux. Okay. So now let us find out the velocities. The velocity is v0 with which it is hitting the surface, and this makes an angle theta naught here. Okay. Similarly, once the flow is deflected in two parts and this flow is coming here, which is this flow is going there. So this is v1, and v1 that is going here is making an angle theta 1 with respect to same horizontal line and going anticlockwise. And if you see this theta 2 or the velocity 2 is making an angle theta 2, that is with respect to horizontal again in anticlockwise. So what we have done, we have taken the control volume and we have found out all the velocities and their directions with respect to a horizontal line, taking the angle anticlockwise from the horizontal line. So our reference frame is constant, our reference direction is constant. So taking this theta at all the locations with respect to horizontal and anticlockwise direction, we can calculate. So this will not create any confusion. Okay, so it has a standard reference frame. So you can similarly always take a standard reference so that you don't make any mistakes. If I take the theta here as with horizontal, I'll take this theta, and if I come here, I'll take the horizontal line on this side and I'll take this theta. It's not going to be correct because you have to keep that uniform. So always it's better to set a standard reference. So now I am measuring the theta anticlockwise from the horizontal surface. Now once I do that, I'll be able to write down the outflow momentum minus inflow momentum and find out the forces. So let us find out the forces in x direction. So what can I do? I can write down the summation of forces in x direction is equals to the outflow momentum minus inflow momentum. What are the outflow momentums? I know this momentum is going out, this momentum is going out. So outflow momentum when I write, first let us say take me v1. So it is rho q1 v1, because the discharge here, here and here, they all three could be different. So I need to find out individual discharge. So I will rather take rho q1 v1 multiplied by v1 multiplied by cos theta. So q1 is nothing but your area multiplied by velocity here, that you can calculate. But rho q1 v1 is going to give you a rho q1 v1 cos theta. Sorry, you have to find out the velocity in x direction. So velocity in x direction is going to be cos theta. So cos theta, if you find out from this theta happens to be, let us say, more than 90 degrees, it will automatically give you a negative sign. Okay, so you don't have to do anything. Now similarly, if I take the cross section 2, that is velocity 2, so it is rho 2 q2 v2 cos theta. Now v2 cos theta will come as positive. Okay, so I have taken the outflow momentums minus inflow momentum, that is nothing but your rho 0 q0 into v0 cos theta. So if I write down this expression, then I will be able to get what is the force that is going to act in the x direction, or summation of forces in the x direction is obtained. Okay, so similarly we can write down the forces in the y direction. I can write down Fy, which is nothing but going to the velocities in y directions are going to be the sine theta components. So same rho 1 q1 v1 sine theta 1. Okay, so yeah, I have written theta 1, theta 2, theta 0. So rho 2 plus rho 2 q2 v2 sine theta 2 minus rho 0 q0 v0 sine theta 0. So these two equations will give you the forces in x and y directions. Once I find out the forces in x and y directions, I can always find out what is the resultant force. It is nothing but square root of fx square plus Fy square. So I can find out the resultant force, also the resultant or the direction angle with which it is going to act. Okay, so that you can find out, let us say angle alpha is equals to tan inverse Fb by Fh. Okay, so now we have seen how this linear momentum equation or linear momentum principle can be applied to solve problems and find out forces so easily. You really don't need to understand what is happening. If I will ask you, you find out the flow properties along this curve, what is the pressure, and integrate and find out the force, it is possibly going to be much more cumbersome and difficult than the way we have found it out right now. Okay, so that's why these simple concepts are very useful and it needs to be understood.